Okay, so this is the continue of how the process synchronizations has been implemented and examples. Okay, so in this section we are more presents about the number of synchronization problems as example in large class of concurrency control problems. These problems are used for testing nearly every newly proposed synchronization scheme. So in our solution to the problems, we use a semaphore for synchronization, since that is the traditional way to present such solution. However, the actual implementation of this solution could be used as text logs in the place of binary semaphores. Okay, so this is a classical problem that used to test a newly proposed synchronization scheme. So antaranya ialah bundle buffer, readers writers problem, and the Dining-Philosophers problems. Okay, so the classic problems bila nak implement synchronization. Okay, so ini happens bila kita nak create the new process of synchronization lah. Okay, so antara problem yang dia dah tested dan only propose adalah bundle buffer problem, readers writers problem, and Dining-Philosopher problem. So yang ni kamu kena faham saja konsep, kamu tak perlu buat coding ke ataupun tak perlu ni, okay? So you have to identify, you are able to explain, okay, apa problems, okay, kalau synchronization scheme ni, okay. So antaranya bundle buffer macam mana, readers writers problem macam mana, lepas tu Dining-Philosopher problem macam mana. Okay, now kita pergi ke bundle buffer problems. Okay, the bundle buffer problem, okay, is commonly used to illustrate the power of synchronization primitives. Okay, so here we present a general structure of the scheme without committing ourselves to any particular implementation. So we only provide the concept saja on how the concepts lah. Dalam the bundle buffer problems, kita akan introduce the producer and the consumer process. Okay, kita akan nampak producer and consumer processes share the data structure. Okay, iaitu dia akan the int will be has in the buffer, and then the semaphore mutex equals to value 1, and the semaphore empty will equals to n to do with the value n, and the semaphore full, okay, will be have to the equal 0. So we assume that the pool consists of n buffers. Okay, we have a numbers of buffers, okay, that hold for one particular item. So the mutex semaphore provide the mutual exclusion for access to the buffer full and initialize to the value 1. Okay, so dia akan initialize lah. So with the buffer full, okay, buffer full, and it is initialized to as a value 1. Okay, semaphore mutex ni initialize je as a value 1. Okay, dalam bentuk buffer full. So the empty and the full, okay, functions, okay, of the semaphore akan count the number of empty and full buffers. So the empty and full ni, semaphore ni dia akan responsible untuk count the number of empty and the full buffer. So the semaphore empty is initialized to the value n, okay, and the semaphore full will be initialized to this value 0. So the code for the producer a process, okay, akan ditunjukkan sebentar lagi, and the code of the consumer process akan ditunjukkan. So kita akan nampak the symmetry antara, okay, this is a construction for the producer process, okay, yang saya cakap tadi, and okay, so producer, wait empty, and the wait mutex, and the signal mutex, and the signal full, and this is the structure of the consumer process. So kita dapati ada symmetry between the producer and consumer. So we can interpret this code as the producer produce the full buffer, okay, producer produce the full buffer for the consumer, or the consumer can producing the empty buffer for the producer. Okay, so this one, okay. Okay, so there's a problems lah. Okay, when you have a multi buffer that run process at the same times. Okay, that is a bounded buffer. Next, okay, we have a readers writers problems. Okay, so suppose the database to be shared among the several concurrent processes. Ini readers writers problems ni banyak berlaku apabila kita nak synchronize data, terutama sekali di dalam sistem ataupun proses yang melibatkan database. Alright, so the suppose database are shared among the several concurrent process. Ini apabila you have a centralized database. Okay, more process share the same database, and some of these process may only to read the database, whereas others want to update. Update contohnya dia nak read Kern or write to the database. So we distinguish between these two types of process by referring to the former as a reader, okay, and the latter as a writer. So obviously we have two readers access, ada dua reader access the shared data simultaneously, not adverse affect to the result. However, if a writer and some other process, okay, have a reader or writer access the database simultaneously, there have been a chaos, okay, or issue. To ensure this difficulty does not arise, okay, there are multiple readers nak read dalam bahasa yang sama dan one single writer nak share the same data at the same time. Okay, so dia akan berlaku ni di sinilah issue lah. To ensure that this difficulty do not arise, we require that the writer have exclusive access. Okay, so apa yang kita buat ialah untuk mengelakkan masalah ni berlaku, kita akan beri exclusive access kepada writer that to the access to the shared database. Okay, kita ada exclusive access to shared the database sebab dia tengah write itu database. Contohnya kalau awak buat sistem, okay, sistem tu, okay, awak tengah update ataupun tengah create database, create table ke, okay, create table, create column, row atau sebagainya. Okay, dalam masa yang sama ada orang nak access the same particular database. So, apa yang terjadi ialah kita akan bagi exclusive access, okay, khas, okay, kepada the writers, okay, to share the database while they writing to the database. So this synchronization problem will refer to as reader writers problem. Okay, kita dah mention dah memang ada problem yang used to test nearly synchronization. So reader writers problem has several variation. Dia ada banyak variasi dia, or di mana dia akan involve a priority. Okay, the simple one is referred to the first reader writer problem that requires no reader be kept waiting unless the writer has already obtained the permission to use the shell object. In the other words, no reader should wait for the other readers to finish simply because a writer is waiting. So another second reader writer problem requires that once a writer is ready, the writer perform its write as soon as possible. In other words, if a writer is waiting to access the object, no new readers may start reading. So a solution to either problem may result in the starvation. So apa yang berlaku dalam problem ni, reader writers ni, dia akan berlaku starvation lah sebab terlalu waiting process, okay, to access the object. So in this first case, writer may starve, because the second case, readers may starve. So for this reason, other variants of the problem have been proposed. So we present the solution to the first reader writers problems. Okay, so in the solution, kita akan provide the reader process check the data structure lah. So the semaphore, okay. So they provide the use a semaphore mutex, okay, in order to read and count. So the semaphore mutex, okay, is common to both reader and the writer. So the mutex semaphore is used to ensure the mutual exclusion when the variable read will be updated. So the semaphore mutex function is a mutual exclusion as semaphore for the writers. So it's also used by the first or last reader that entered or exit the critical section. Okay, so the reader writers problem and its solution has been generalized to provide the reader writer log on the some system. So the acquiring acquiring a reader or writer log requires specify the mode of the log, either to read or write access. So when the process wish only to read share data, then dia akan request the reader writer log in the read mode. So a process that wish to modify the share data must request the log in write mode. So the multiple processes are permitted to concurrently acquire the reader writer log in the read mode, but only one process may acquire the log for writing. So exclusive access is required for the writer. So that is it. Okay, so ini contoh dia share data. Okay, they have the data set. Okay, so the semaphore for the writer mutex initialized to 1, and then semaphore mutex initialized to 0. So they ada will count. So this is structure of the writer process. Okay, the code, and this is a structure for the reader process. Okay, so the solution they can be a various lah. Okay, so yang macam saya explain tadi, solution provide can result situation. Okay, never writes. Okay, and it's referred to as a surface reader writer problems. Okay. Okay, now we go to the third one, which is the Dining-Philosopher. Ini seronok sikit. Okay, sebab dia macam dining. Okay, macam okay. Dalam Dining-Philosopher ni, apa yang kita buat ialah kita akan consider 5 philosopher. We have a 5 philosophers here. 1, 2, 3, 4, 5. Okay. 5 philosophers who spend their life thinking and eating. Okay, so this is a philosopher. Okay, kita bagi dia spend their life on thinking and also eating. Alright, so the philosopher akan share a circular table. Okay, they have a circular tables here. Alright, that surround with the 5 chairs, and setiap philosopher ni each belonging to one philosopher. Okay. So in the center of the table, we have a bowl of rice, and the table is laid with a 5 single chopstick. Okay, setiap ni dia ada 5 chopsticks. Okay, 5 single chopsticks, and apa yang berlaku ialah bila philosopher tu nak berfikir things, okay, she just not interact with her colleague. So bila dia tengah berfikir ke, dia tak akan interact with the colleagues. Okay. From the time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks that are closest to her. Okay, antara left and right lah. Okay, so a philosopher may pick up only 1 chopstick at a time. So obviously she cannot pick up a chopstick that is already in the hand of the neighbor, of course. Okay, so macam kita makan lah. Okay, makan in the Chinese food restaurant ke apa ke. So kalau orang tu dia nak ambil chopstick, dia dah ambil kalau kanan, dia tengok kan yang sebelah tu kan jiran kanan dia dah ambil chopstick dah gunakan. So dia tak boleh ambil lah. So dia ambil yang kiri. So kalau yang kiri pun dia dah ambil, dia kena tunggu. So tu maksud dia. So when the hungry philosopher has both the chopstick at the same time, she eats without releasing the chopstick. So when it's finished eating, she put down the both chopstick and start thinking again. Okay. So apa yang kita boleh gambarkan, okay, kita boleh gambarkan ialah in the case of philosopher, the share data. Okay, kita anggapkan the bowl of rice ni is like a data set, and the chopstick ni yang dekat setiap philosopher ni, dia adalah sebagai semaphore chopstick. Okay, that initialized to 1. So Dining-Philosopher problem is considered as a classic synchronization problem, neither because of its practical importance nor because computer scientists dislike philosophers, but because it's an example of large class of concurrency control problem. So it is a simple representation of the need to allocate the several resources among several processes in a dialogue-free and starvation-free manner. Okay, so ini yang berlaku lah. Okay, so kita bayangkan lah, philosopher ni processor lah. Proses. Okay, and then chopstick ni dia punya semaphore. Okay, rice ni macam dia punya resources lah. So bila dia keep thinking, alright, dia nak interact with the other. Okay, tapi kalau bila dia perlukan, macam contoh dia nak makan, so dia perlukan resources lah. Okay, so dia perlukan resources like a chopstick tu as a part of dia punya resources in order rice ni, untuk dapatkan rice. So dia nak dapatkan rice ni, So dia kena pakai chopstick. So kalau chopstick tu telah digunakan oleh orang lain, maka dia have to wait. Okay, so berapa lama? Bergantung kepada philosopher. The philosopher or the neighbours philosopher dia. So dekat sini, that's why dia akan berlaku adalah deadlock. Okay, so deadlock ataupun starvation lah. Dia akan berlaku starvation. Kenapa? Okay, contoh kalau kat sini, okay, they have a philosopher. So kat sini dia nak makan. Okay, so they have to access data ataupun resources. Contoh rice ni, imagine rice ni as a data set. So katakan this particular philosopher, dia nak ambil sebelah kanan, dia tengok chopstick dia dah diambil orang. Sebelah kiri pun chopstick dia telah digunakan oleh neighbor dia. Kiri kanan. So what happened here? Have to wait. So how long the wait? Have to wait indefinitely. So dekat sini akan berlaku starvation lah. Okay, they have to wait both. Okay, baru dia boleh access to that particular rice. So this is a problem. Okay, that's why we call a dining philosopher problems. Okay. So this is a structure of philosopher. So dia nak kena tunggu chopstick. Eat for a while, and then yang ni dia kena lepaskan chopstick lah. Okay, so kalau dia thinking, dia dah habis makan, dia akan letak, release lah dia punya chopstick sebenarnya. So chopstick tu ibarat dia punya semaphore lah. Okay. Okay, so they have to monitor. So okay, so the solution is to represent each chopstick with a semaphore. So first try to grab a chopstick by executing a wait operation on that semaphore. So she releases the chopsticks by executing the signal operation on the appropriate semaphore. So bila dia share data lah, let's wait. Okay. So the several remedies for this deadlock are replaced by, okay, kita ada banyak cara, okay, untuk ini. Antaranya ialah monitor the solution. Okay. So antaranya ialah kita monitor the solution. So sebelum tu kita akan tengok macam mana deadlock can be replaced. Okay, how to solve the problem on the deadlock dalam dining philosopher ialah, okay, kita allow most of four philosophers to be sitting simultaneously at the table, and allow philosopher to pick up her chopstick only if both chopsticks are available. Okay, so kita bagi condition lah, okay, untuk elak berlaku deadlock. Okay, deadlock ni berlaku bila dua-dua akses benda yang sama dalam satu masa. So the philosopher, apa yang kita buat, at most four philosophers ni simultaneous at the table, allow the philosopher to pick up her chopstick only if bila both chopstick tu available, kiri ataupun kanan. Okay, contoh macam they must pick up in the critical section lah. Okay, and use a symmetric solution di mana that is, and the odd number philosopher pick up the first left chopstick and then the right her right chopstick, whereas and the even number philosopher pick up her right chopstick and then her left chopstick. So this solution can provide problems, can ensure the freedoms of the deadlock. Okay, note however, there are any satisfactory solution to the dining philosopher problem which can guard against the possibility that one of the philosophers will starve to the death. So the deadlock-free solution does not necessarily eliminate the problem of the starvation. So deadlock-free tak semestinya solve the problem of the starvation. So another solution is provide the monitoring solution to the dining philosopher, di mana we have example of such error that use a counter in our solution to producer and consumer. In the example, the timing problem happened only rarely and even the counter value, so to be reasonable but off by only one. So nevertheless, the solution is obviously not acceptable. It is reason the semaphore were introduced in the first place. Okay, unfortunately, such timing errors can still occur when the semaphore are used. To illustrate how we semaphore solution, so the critical section problems, all the process share the semaphore bevel method, which is initialized to 1. Okay, and each process must execute wait text before entering the critical section and the signal afterwards. Okay, so this is how the monitoring lah. Ini dia punya tak perlu ni. Tapi you kena tahulah, kalau dia stay hungry, so they have the taste, okay, right, so not to eating. So they have to pick up. And then kalau put down, maksudnya dia tengah thinking. So dia kena monitor benda ni lah. So dia monitor, dia provide thinking, hungry and eating. So kalau thinking, dia kena like, okay, the neighbors tu have test sama ada left, sebelah kiri atau kanan neighbors tu are thinking, and then they have a test. Tapi kalau in the state of hungry, so dia kena bagi. Okay. So this is how they do in this test. Okay. Tengok je. Okay. Tak perlu nak ni sangat sebab you kena faham the Dining-Philosophers saja. Okay. So ni contoh dalam Windows how they use process synchronization dalam Windows. Mana they use a spin lock and also provide the structure objects. Okay. Ini boleh baca sendiri lah. Okay. Dalam Windows macam mana Windows provide the process synchronization. In dalam Linux, okay, Linux synchronization dia banyak menggunakan semaphores and also atomic integers. Okay, and they use example of reader writers problem version 4 di single CPU. Alright, ni solver POSIX, okay, synchronization. So yang ini memang multiprocessor lah. Okay, so dia akan pakai method sort and also semaphore dalam synchronize, okay, between the different operating system. Okay, you have to tengok macam mana Java do a synchronization. So dia menggunakan konsep yang sama, method sort, semaphores, alright. Macam mana dia synchronize. Sebab Java synchronization ni banyak kita gunakan. Contoh kalau ada Android, dia banyak synchronize with the Java library. Okay, kalau yang mana pakai developers yang running Android, so dia kena synchronize dia punya Java library. So dia punya threads, we will try to acquire the log, okay, in the intercept. So dia kena set benda ni. So this is tak perlu hafal. Okay, just have to look macam mana Java implement. So Java dia test dia punya process synchronization guna bounded buffer. Okay. So with condition variables, okay. Ni alternative approach lah. Ni contoh, ni tak, ni just additional information about the example of process synchronization is being implemented. Antaranya transactional memory, OpenMP, okay, functional programming. Okay, so that's all for the process synchronization topic.